Okay, our learning target for last night's video was to identify phase changes in a chemical system, and our success criteria is to describe the kinetic molecular theory of matter and how it relates to phases of matter, and to explain how matter can change from any one phase to any other phase, and how these changes require energy. Probably at one time or another, you've had a discussion, whether it was in physical science, if you took it here at Salina High School, or another physical science, you've discussed kinetic and potential energy. Now, the kinetic energy is dealing with the energy of motion. So, when we start to talk about the kinetic molecular theory of matter, we're actually talking about the motion of the molecules or the motion of the atoms. All particles have energy, and the energy varies depending on the temperature of the sample of matter. So what do you think? Where do you think that matter is moving faster, if it is a gas or if it is a solid? If you said gas, you were correct. Okay? You were correct because the matter of gases are moving faster than that of liquids and solids. And we'll discuss it here in a little bit. Okay? This determines whether a substance is a solid, a liquid, or a gas. So, depending on the temperature, we know depends on what state that matter is in. Solid particles have the least amount of energy. Gas particles have the greatest amount of energy. The temperature of a substance is a measure of the average kinetic energy of the particles. So, we increase the kinetic energy. We increase the movement of the particles. We increase the temperature. Therefore, we get the solid, liquid, and the gas. Obviously, doesn't steam, which is water vapor, don't you think that has a little bit higher temperature than what ice does, which is a solid? A change in phase may occur when the energy of the particles are changed. There are spaces between matter. The average amount of empty space between molecules gets progressively larger as the sample moves from solid to liquid to gas. So, if we have a solid, we do not have as much empty space between the molecules. If we have a gas, we have a lot more empty space between the molecules. There are attractive forces between atoms and molecules, and these become stronger as the particles move closer together. So, thinking, we just said that solids had less space than gases. So solids are closer together than gases. So these attractive forces are greater with solids than they are with gases. The attractive forces are greater with liquids than they are with gases. This is what we call intermolecular forces, which you also watched a video on last night. Those attractions between the molecules. Now, what I would like for you to do is I want you to write this down. I'm going to give you a little bit of time to write this question down because this is our very first example of these types of problems. And believe me, you're going to want examples to go back and look upon. This energy change at phase change is something that students tend to struggle with. That's why I'm making this new video. Hopefully I can alleviate those struggles. The question states, how much energy does it take to raise the temperature of 19.0 grams of water from negative 13.0 degrees Celsius to 55.0 degrees Celsius? So this is the question that we are going to answer. But before we do so, we're going to talk about this diagram right here. Now, hopefully you have this diagram somewhere in your notes. I've got a note up here to put this diagram on Google Classroom. So I'm going to drop this on your Google Classroom sometime today. But if you look up here on my axis, I have temperature and I have time. So my two axes are temperature and time, and I have what I call 5 different areas, and I've labeled these 5 different areas with Roman numeral 1, 2, 3, 4, and 5. Now we're going to talk about these 5 different areas, and we're going to do it in terms of water. Now, the question that we just had said that we had 19.0 grams, and it went from a temperature of negative 13 degrees Celsius to 55 degrees Celsius. Well, when we're dealing with water here, ladies and gentlemen, okay, we are going to start out right here, and this is going to be our negative 13. It's going to be over here in area number 1. Okay, so area number 1 is going to be at negative 13 degrees Celsius. Now, how do I know that? Well, I know that when I have a phase change, when I'm going from a solid to a liquid, I have that plateau. And this is the same plateau that we're seeing right here in area 2. So this plateau here is represented for water at 0 degrees Celsius, because that is my freezing point, that is my melting point. So if I have something in area 1, it is ice. I can see right here that I have the plateau. That plateau represents the phase change. Now let's stop and think. At the phase change, the temperature is 0 degrees Celsius. I'm going to tell you why there's not a change, okay? Why the temperature is not increasing. Because when we have those intermolecular forces of the solid, we have to break those forces. So when we are heating it, even though we didn't stop heating it, all of the energy from the heat is required to break those intermolecular forces between the solid. So you're going to see that plateau at 0 degrees Celsius. When you come in to then area number 3 here, area number 3 is going to start right here, and this is going to be a liquid. So all of area 3 is going to be a liquid until we hit that plateau again in area 4. Now that plateau in area 4 is going to be the boiling point. What does water boil at? What temperature? 100 degrees Celsius. Good. So this is right here going to be 100 degrees Celsius. Once again, it flat lines there, it plateaus because we need to use that energy to break the molecular forces that are between the water molecules. And once we break those forces, they spread out even more. There's more empty space. They turn into a gas. So anything over here is what we would call steam, or it could be called water vapor. So area 5 is going to have steam or water vapor. So that's an explanation of our different areas. Now, when I get to be right here, okay, that is when I start to change from a liquid to a gas. That's at 100 degrees Celsius. So what is over here? Once I start going up, what's that temperature going to be? What's that temperature going to be? Over 100, right? That's going to be greater than 100. So when I'm talking about going from negative 13 degrees Celsius to 55 degrees Celsius, where's 55 going to be? What area? It's going to be area 3, right? Because area 3 went from right here, 0, to up here, 100. So when we're going to get somewhere in here, are 55 degrees Celsius. Now, just putting this together, explaining all of the areas, hopefully we have a better understanding. Because when I have area 1, it's all going to be a solid. Area 2 is going to be a phase change. Area 3, it's going to be a liquid. Area 4 is another phase change. And then finally, area 5, it's going to be a gas. So keep that in mind. Keep that in mind, because when we come back to our problem, this problem right here, if we look, we start off at negative 13 degrees Celsius and we go to 55. So when I'm talking about my areas, I'm doing area 1, I'm doing area 2, I'm doing area 3. Do we get to area 4? No, because we stop at 55. Do we get to area 5? No, because we stop at 55. We don't even get all the way through area 3. Now, what does all of this mean? Well, you can see that on my chart up here, I have 5 different equations to calculate Q. And Q is the amount of energy, and we're going to label that in joules when we do these. Okay? So our label will be joules, the amount of energy. So we're going to we could have to do 5 different calculations, but they're not very tough calculations. I'll show you here. But we could have to do 5. In this instance, we're only going to have to do 1, 2, and 3 areas because we go from negative 13 here to 55. So let's talk about these. Area 1. Area 1, Q is equal to M times C of the solid times delta T. So we have to figure out 3 things to figure out the energy. Now, if you are doing these wrong, if you are struggling on your WebAssign, look at your temperature, because temperature is where things get messed up. That's where you're going to make your mistake. And the reason being is we know what our mass is. For this particular question, what's the mass? 19 grams, right? 19.0 grams. So our mass is going to stay the same for all these. Delta, or excuse me, not delta, C of the solid. Where do I get C of the solid? Well, ladies and gentlemen, the C of the solid is going to come from this chart that I gave you. Now here is the heat of vaporization and fusion. That's not the one we have. We're going to use this one right here. And if you look down here, we have water. And it says ice, it says a liquid, and it also says steam. So we're going to be using these values right here. Ladies and gentlemen, if you look at my chart, I have those values highlighted so I can find them very easily. These are specific heats. C is the specific heat. So when we're talking about the specific heat of a solid, and we're dealing with water, that solid is going to be ice, and that specific heat is going to be right there, 2.100. So as I come back to my diagram here, and I look at this and I say, okay, M is equal to 19.0 degrees Celsius. I'm going to multiply that by my C of solid. Well, my C of solid, I just said, was 2.100. And if you look at the label up at the top of the column, it's joules over grams times degrees Celsius. Now, the last thing I have to find is the toughest. Okay? Oh, yeah, you're right. The 19 should be grams. My bad. The 19 should be grams, so let me get this changed maybe. My eraser on my smart board doesn't work very good. And it's not going to work for me. So let me see if I can. Get that off of there. Come on. All right, we're just going to change it. Maybe. Maybe my whole board is not going to work now. Let me see if I can reset it. We got it. There we go, 19.0 grams. Okay. Now, the last thing I have to find is I have to find delta T. So when I do that, I'm going to do this down here in the corner. Delta T is equal to the T final minus the T initial. Now, like I said, this is the toughest part. Usually people don't struggle with the initial temperature. Where did we start at? What temperature? Negative 13. So our T initial is going to be negative 13 degrees Celsius minus, what is our T final? Now, most people look at this and say our final temperature is 55. But that is incorrect. And that's where we get the rub. Why is it not 55? Because we're in area 1. Where does area 1 end at? What temperature does area 1 end at? 0. Okay? So, what is 0 minus a negative 13? It's 13. So my temperature is 13 degrees Celsius. So, does everybody understand that part about temperature? Because that's the big part. That's where everything gets screwed up. Area 1, temperature ends at 0. Now, when I go through and I do my math, I'm just going to get this out of here so that I can have my Q is going to be equal to, I did all my math and it came out to be 518.7. And if I look at my label, I have grams cancel here. I've got degrees Celsius in top, bottom here. So my label is going to be joules. So this is telling me that in area 1, I need 518.7 joules. Luke? I'm not going to sig fig it until the end, but we will. Okay? I'm going to leave it just like this and sig fig everything at the end. Now, my next, area 2. Okay, I've just finished my area 1. I'm going to area 2. Now, area 2 is a plateau, right? It is a phase change. Does the temperature change on that plateau? No. So we cannot use temperature in our calculation because it's not changing. So what we are going to use is Q is going to be equal to the mass times the H sub F. Now, what do you think H sub F is? It is the heat of fusion. Where do you get the heat of fusion? Once again, let me come back here. Okay. Let me come back here and get on to this diagram here. And here we have heat of fusion. So the heat of fusion of water is right here. 333 joules per gram, if you look at the label up top here. Joules per gram. Now, just showing you, because I'm not going to come back here later, when we get to the heat of vaporization, it's going to be right here, 2,260. All right? So those numbers aren't changing if we're dealing with water. So when I have my Q is equal to M times H sub F, well, once again, my M is 19.0 grams. My HF is going to be 333 joules per gram. So I have a gram on top, a gram on bottom. That's going to cancel. So I'm going to have my Q labeled in joules, and I'm going to multiply those two together, and that's going to get me for area 2. My Q is equal to 6,327 joules. Now my third area, that area is where we have the liquid. So my mass, once again, is going to be 19.0 grams. My C of the liquid, where am I going to get C of the liquid? What do you think? On our chart, what is my specific heat for a liquid? What is it? 4.186. And my label, joules over grams times degrees Celsius. And once again, here's that tough temperature part. That tough temperature part. Delta T is the temperature final minus the temperature initial. Well, in area 3, where did we start? What temperature? We started at 0, right? Where did we end at area 3? Remember, we didn't go all the way through through area 3. We stopped at 55. So what's 55 minus 0? 55. So our temperature is going to be 55.0 degrees Celsius. So I'm going to get this temperature out of here so that I can put my Q. So Q, when I did my math, my Q equals 437. 4.37. Grams cancel. Degrees Celsius cancel. I get joules. So now, ladies and gentlemen, I've calculated my energy for all 3 of my areas. Now what I need to do is I need to go back and say, okay, my total energy. My total energy. Well, there's 1. There's area 2. There's area 3. Did I have a 4 and a 5? No, so those are nothing. So when I added all 3 of those together, I got 11,220.07 joules. And what you're going to have to do on WebAssign is you're going to have to convert that to kilojoules. How do I convert to kilo? I jump my decimal point 3 to the left. So when I do my sig figs now, Luke, when I do my sig figs, I'm going to go back to my original problem. And if you remember, the only values I was given is 19.0 grams, which is 3 sig figs, negative 13.0 degrees Celsius, which is 3 sig figs, and 55.0 degrees Celsius, which is 3 sig figs. So when I sig fig this to 3, I'm going to get 11.2 kilojoules, and that's going to be my answer. So what does this tell me? Well, to get 19 grams of ice from a temperature of negative 13 degrees Celsius to a temperature of 55 degrees Celsius, I'm going to need 11.2 kilojoules of energy. Now, what I want you to do next is copy this down, because this is the next example that we are going to work. It's a little bit different, so I'll give you a little time to copy this down. How much energy is released when the temperature of 5.00 grams of water vapor goes from 105 degrees Celsius to negative 10.3 degrees Celsius? So let's stop and think as we're talking about phases. Where are we starting at? Okay, what area? Area 5. Okay, what phase do we have in area 5? A gas. Where are we ending at? Area 1. What phase do we have in area 1? A solid. So we're going from a gas to a liquid to a solid. Now, we are going the opposite way because we are starting here in 5 and we are ending here in 1. So that means that we are releasing energy. Okay? Because we're not getting hotter, we're getting colder. Correct? Our temperature is going down. So we are releasing energy. So I'm going to start up here at, what was it, 105 degrees Celsius, right? And we're going to end down here at negative what, 10? 10.3 degrees Celsius. So we're going to go through all 5 of our different areas, starting with 5. Now, it's going to be just slightly different because as I look at right here, my Q is equal to my M, my C of the gas, the delta T. Let's think about our delta T. Delta T is T final minus T initial. Where did I start at? 105 degrees Celsius. In area 5, where do I end at? 100. Because that's where my phase change is. So what's 100 minus 105? My delta T is going to be negative 5 degrees Celsius. Now, when I plop this up here, I do in fact have that negative 5 degrees Celsius right here. Now, all that negative is telling you, ladies and gentlemen, is that the energy is released. Okay? The negative tells us that the energy is released. So, my M is 5.00 grams. My C of a gas is 2.010 joules per gram times degrees Celsius. Once again, where did I get that C value? Off the chart. Good. And my delta T is negative 5 degrees Celsius. So when I did my math, I got negative 50.25 joules. And the negative tells me I'm releasing energy. Now, when I go to area 4, area 4, Q is equal to M H sub V. Well, what's my M? Once again, that's going to be 5.00 grams because my mass is going to stay the same. Where do I get HV? My chart. What is my HV for water? 2,260 joules per gram. Everybody understand where I got that? Now, let me ask you this. We're releasing energy, right? We're releasing energy. So when we do that one, we have to make this a negative value. So I have to signify right here with that negative that we are releasing energy. So when I do my math, I take 5.00 grams, I multiply it by negative 2,260, and I got a value of negative 11,300 joules. Moving on down to area 3. In area 3, we have Q equals M, C of the liquid, delta T. Well, what's my value for M? 5.00 grams. What's my value for C of a liquid? 4.186 joules over grams times degrees Celsius. What's my delta T? What's my initial temperature? Where did I start? Where did I start? 100, right? In area 3. Where did I end? 0. So what's 0 minus 100? Negative 100. There we have all of our data. When I did my math for these, I got negative 2,093 joules. As we go to area 2, we know that Q is equal to MHF. But we need to make sure, since we're releasing energy, we do what with our HF? Make it a negative. So my M is 5.00 grams. My H sub F is negative 333 joules per gram, to give me a total of negative 1,665 joules. Area 1, our final area. Q is equal to M, C of the solid, delta T. M is 5.00 grams. What is the C of the solid? 2.100 joules per gram times degrees Celsius. What is my temperature? Well, ask yourself, where did I start? I started at 0, right? Where did I end? Negative 10.3. So what's negative 10.3 minus 0? Negative 10.3. And I'm telling you once again, for at least the 5th time, maybe more, if you screw these up, where are you messing them up at? The temperature. Look at your temperatures. Okay? You're going to come up to me on your WebAssign, and it's going to be on a quiz. And you're going to say, I can't figure out where I'm messing up at. Where should you be looking at? Your temperature. Because that's where everybody messes these up at. Now, when I did my math, I came up with negative 108.15 joules. So my final total energy is going to be taking all 5 of my areas and adding them up to give me a negative 15,216.4 joules, or negative 15.2164 kilojoules. When I take that to 3 significant figures, I get negative 15.2 kilojoules. And what does the negative tell you? Energy is being released. Now, we're not done yet, because I've got to show you one last type of problem, and this was missed a ton on one of the quizzes. So, let's talk about this one. I'll give you a second to write it down. How many grams of ice at 0 degrees Celsius and 760 millimeters of mercury could be melted by the addition of 2,500 joules of heat? Now, as I'm looking at this, what am I doing here? What's happening to the ice? It's melting, right? Well, where here do I have melting occurring? Area 2, right? So, I know that since I have melting at area 2, here's the guy I'm going to use. So, Q is equal to M times H sub F. Do I know what H sub F is? Do we have any idea what H sub F is? Yeah, why do we know what H sub F is? Because it's on our chart, right? H sub F is 333 joules per gram, right? How much energy do we have? 2,500 joules. Can I solve for mass? Yeah. I'm going to take both sides and divide it by 333 joules per gram. My joules is going to cancel, so I'm going to have a mass in grams. When I take 2,500 divided by 333, it gives me a value of 7.50750. I've got plenty of sig figs there, but I come back here, okay? I'm not going to use 760. That was unneeded, okay? I'm going to use this one right here, which has 4 sig figs. So, once I round this, that's going to tell me that if I have 0 degrees Celsius, I have ice, I have 2,500 joules of energy, I can melt 7.508 grams of ice.